Today's webinar features the paper Air Data Fault Detection and Isolation for Small UAS using Integrity Monitoring Framework. This was published in the fall issue of Navigation in 2021 and was written by Dr. Carrie Sun and Dr. Demos Gebra-Xavier from the University of Minnesota Twin Cities. Today's webinar is being presented by one of the paper's authors, Carrie Sun. Carrie obtained his MS and PhD degrees in aerospace engineering from the University of Minnesota. He also attended California Polytechnic State University in San Luis Obispo for his MS in economics and bachelor's degree in aerospace engineering. His main expertise focuses on synthetic air data systems, state estimation, control for small unmanned aircraft systems, as well as other autonomous vehicles. He's currently working as a lead state estimation and controls engineer at Virgin Hyperloop based in Los Angeles. We greatly appreciate Carrie's time and the work that he put into the webinar. Following his presentation, he'll accept questions from the audience. To ask a question, please click on the Q&A box on your Zoom viewer. So thank you for being here, and now we'll turn it over to Carrie.
Thanks for the kind introduction. So my name is Carrie. Today I'll be presenting work done by my former PhD advisor, Demos, and I at the University of Minnesota. And topic of today is about air data fault detection and isolation for small unmanned aircraft system using integrity monitoring framework. Before going to my research, I'd like to first acknowledge the people that supported me over this project. First, I'd like to thank my advisor, Demos. He has been very helpful and supportive overall. Also, I'd like to thank Todd Colton of SENTERA, who provided the actual flight data for this project. I'd like to thank Minnesota Invasive Terrestrial Plant Center for their financial support. And finally, I'd like to thank the Institute of Navigation for this wonderful opportunity and the audience for attending this webinar. Before diving into the topic, I want the audience to understand the final goal of my research is to develop reliable air data solution for small unmanned aircraft systems. And to achieve this goal, we believe air data software needs to satisfy 4 levels of requirements, which include accuracy, continuity, integrity, and availability. My earlier work has focused on air data sensor calibration and estimation. And in this recent paper, we focused on air data fault detection and isolation. And with those developed algorithms, we believe they can be used to provide a reliable air data system for small UAS that are fault tolerant, safe, and certifiable. So what is air data? Air data contains important quantities such as speed, orientation, altitude, temperature, and here we're mainly concerned with 3 important quantities: airspeed, angle of attack, and side slip. And those 3 quantities usually define the flying envelope. Airspeed is speed of the vehicle relative to the air, and angle of attack and side slip are the orientation angles with respect to the flow direction. The air data ensures the safety and the performance of an aircraft. Here are some examples of a typical air data system used on various aircraft, range from commercial aircraft, electric vertical takeoff, to small UAS and quadcopter. The complexity of an air data system is dictated by safety and regulation. For example, the Airbus A350 needs multiple air data sensors to ensure stringent safety requirements, whereas a X-wing plane at the moment only requires 1 single heated pitot tube. Something in the middle will be like a small aircraft taxi, such as the one on the lower left corner, Joby, that I didn't talk to them, but based on the picture, you can see there's an air data boom. Also, there are 2 pitot tubes. So those examples shows you how multiple and versus single air data system design. For smaller UAS, single air data system sensor is often used because there's a size, weight, and power constraints for on the vehicle, which is one of the reliability issues faced for those small UAS. Just to give a bit of insight on air data system requirements, here is a comparison between commercial aircraft and the unmanned air carrier. Those requirements are usually set by the regulatory agencies such as the Federal Aviation Administration and the FAR in the United States. The commercial aircraft air data system needs to follow Part 25, which is the airworthiness standards for transport category airplanes. There are different types of air data system requirements, such as number of sensors, accuracy of the sensors, and the functional requirement. For example, the commercial aircraft needs to have more than 2 same type of sensor to ensure high reliability, and the probability of the failure has to be extremely small. On the other hand, there's no specific air data system requirement for the small UAS. The only existing requirement for right now is for air carrier, such as a Google X-Wing and a UPS Forward. However, also there are some functional requirements are not specified. It is envisioned there are going to be more specific requirements will be defined for the small UAS in the near future. And it's our goal to design a reliable air data system to see the feasibility of those future requirements. Just showing earlier, high reliability is obtained by usually having multiple redundancy sensors. This approach is usually called hardware redundancy. For example, the commercial aircraft Boeing 787 has 4 independent air data systems. However, there still exist issues with hardware redundancy. First, a reliable air data sensor is often very expensive, and they also can suffer a common mode failure, such as icing. And second, it is infeasible for small UAS to have multiple air data sensors, and due to the size and weight and power limitation. So how do we ensure the level of reliability of small UAS, such as the one on the right, without hardware redundancy? This can be done by something so-called analytical redundancy. In particular, in the domain of air data system, it is often referred as a synthetic air data system, which fuse information from sensors such as GPS, IMU, and aerodynamic model to come up reliable air data estimates. In fact, synthetic air data system has been implemented for Boeing 787. However, analytical redundancy faces a different set of challenges when applied to small UAS due to low-cost sensors used on those aircraft and different environment it's operating. So the key question I would like to address in this topic today is, can analytical method be used to improve safety from requirement point of view? In other words, in the case of a failure, how can we show analytical method is reliable in the probabilistic terms? And this paper provides a fault detection method through integrity monitoring framework that bridges between the requirements and the algorithm. Before going to the fault detection method, I'd like to motivate why air data system on small UAS is prone to fall. On the right, it is showing a typical low-cost ADS used on a small UAS. It only consists of a pitot tube, a transducer, and some plastic tubes. This air data system is simple but prone to fall. One of the most common fall mode is water blockage fall. This fall often occurs during a foggy and raining day, which can be a safety threat. we were able to obtain two recorded faulty airspeed data with no water blockage fault. They both experience a very similar drop at the end of the flight when the pitot tube is actually plugged. The slope of those two were calculated to be 2.5 meter per second square and 3.5 meter per second square, which are those numbers are being used for develop the fault detection algorithm. In the past, air data fault detection and isolation method can be loosely separated into three categories: model-based, model-free, and data-driven methods. Model-based and model-free usually rely on a dynamic or kinematic relationship to detect faults, and data-driven method usually uses data to figure out to reject inconsistent measurement. However, those existing methods usually focus on the algorithm side, and we want to use a method that focuses on system requirement. And we believe integrity monitoring framework is an approach that allows us to do that. So what is integrity monitoring? So integrity monitoring is a framework that uses statistical tests with redundant measurement to detect errors. Also, it's able to alert the system if there's a fault. It also provides a statistical bound to protect its state based on the system requirements at various scenarios. Integrity monitoring has developed for many GNSS applications. One of the known example is a civil aircraft precision landing system. The basic idea is demonstrated with the figure on the left, where an aircraft uses a redundant range measurement to position itself and protect its error epsilon using something called protection level bound against its predefined alert limit. It also has a detect function that is comparing to a certain threshold. So both detection function and the protection level bound are derived from the requirements, which is a nice thing about the integrity framework. In this study, we try to leverage the technique used in the integrity framework to assure the reliability of the air data system on the small UAS. We want to, in particular, we want to protect air against water blockage fault, and also protect its alpha air data estimates. However, the technique cannot be easily transferred. There are many challenges showing here. For example, in the case of a GNSS landing system, the system is usually always observable, meaning you always have this measurement, and the common filter states it's always observable, and the linearization is always valid. But this is not the case for many other applications, including the air data system we're having here. And so we proposed a dual pitot tube air data system design that uses two pitot tubes, one IMU, one GPS receiver, where each pitot tube is coupled with a GPS and IMU as a filter to provide synthetic air data estimate, denoted as SAS. The SAS is used as a base for fault detection. Each SAS provides estimates, and the fault detection box here will check if there is a fault. If there is a fault, the system will raise a flag, and the isolation is achieved by looking at the flag. This detection, this design also provides protection level bound for the synthetic air data estimates. Since the focus of today is on fault detection, I will just have one slide to cover synthetic air data system. So the synthetic air data air data estimator is basically a 15 state INS GNSS loosely coupled extended common filter augmented with 3 additional wind states and 1 additional airspeed measurement. It basically fuses IMU, GPS, airspeed to estimate position, velocity, attitude, biases, angle of attack, angle of side slip, and 3D wind. For this estimator to work, however, the following condition has to be met. First is the airplane has to be constantly accelerating, which is usually often enabled by the heading change. And the second condition is the wing has to be quasi-static. In other words, it has to be actually slow varying. If it's changing so fast, this estimator capability degrades a lot. So that's a synthetic the SES wanted to talk about. So in the fault detection design by integrity monitoring framework, it has a few procedures. First, we need to define performance requirements and the fault we want to protect against. Then we need to design a appropriate threshold and detection function D and the protection level. And once all of those metrics are designed based on the requirements, the state of interest can be checked in real time to determine faults. The flow chart on the right is an example of checking the validity of the state estimate. We have 2 levels of integrity check. Here, the availability check and the fault detection check to see whether the state estimate is valid. And lastly, we check the state error to see, for example, in this case, position estimate, it's correct. In the next few slides, I'll walk you through all of the procedures briefly for our pitot tube air data system design. So first, we have the following requirements for our system: integrity, continuity, and something called a minimum detectable error, or MDE. Integrity can be characterized by a parameter called integrity risk, which is equal to approximately, in our case, equal to probability of misdetection. In this case, it's the probability of undetected pitot tube failure. The continuity risk equals the probability of false alarm. And in this case, it means the probability of issuing alarm when there is no failure. The MDE is a measure for a minimum size of the error that can be detected with certain probability of false alarm and misdetection. This MDE can be computed based on the fault model. In order to compute this, we need to define what type of error we're facing. So in this case, we modeled our water blockage fault as a ramp fault. And the slope of the ramp was defined to be 2.5 meters per second square based on the real data. We also define a allowable error. And this is done by assuming that this average operating airspeed is about 17.5 meters per second. And the stall speed is about 10 meters per second, which gives the range about 7.5 meters per second. And this number just means that if the aircraft drops below stall speed, we'll assume, if the detection function hasn't detected this magnitude of fault, then the detection algorithm fails to, it's basically ineffective. So, and this also translates to a 3 seconds detection time. So basically, this calculation gives an upper bound on the minimum detectable error. So then in the next slides, I'll show how the minimum detectable error is calculated. In order to determine the minimum detectable error, MDE, and the threshold, something called a detectable operating characteristic curve is used to understand the trade-off between false alarm and misdetection and the effectiveness of the the threshold of T here. The DOC curve is obtained by plotting various misdetection and false alarm rate at a different threshold and at various bias levels. It is visualized here for a fixed level bias here. Moving the threshold, it's like moving the magnitude on this line defined by the misdetection, the false alarm. And the DOC curve basically help us find a appropriate threshold and for the fault we want to protect against. So we generated this DOC curve based on various fault levels. And the color here represents the fault size. And the higher the color is, the bigger the bias is. So for example here, for a given performance requirement, such as false alarm 10 to the -5 and misdetection 10 to the -4, the minimum detectable error is calculated to be 5 meters per second, which also translates to a 2 seconds detection time. So on the right column, you see here, basically it's the allowable error, right? Usually it's defined by the error frame. So as you can see that the derived requirements does not exceed the allowable, which means for a particular set of performance here can be satisfied with the design threshold before the UAS fault detection becomes unrecoverable. Once the requirements set, we need to select an appropriate detection function. Since our filter is a common filter based estimation, we have the two following typical choices, the innovation test and the residual test. Innovation test is a standard KF chi-square test, which uses the prior estimate to form an innovation vector. The residual test requires number of measurements that's greater than the number of states, and usually in every snapshot. And typical residual, but this residual test is not going to work for our case because we have measurements at each time step less than the number of states. So we actually proposed a sequential residual detection function where now the degree of freedom problem can be satisfied if we have a window of measurement. We also showed that our detection function is a function of the observability matrix here, which can be analyzed to assess the observability of the system in real time. Lastly, we need to design a protection level bound. The purpose of the protection level bound is to provide some kind of guarantee for the state error. And the alert limit is the maximum error that can be tolerated. Mathematically, it can be expressed as the probability of the state error greater than the protection level bound that is less than probability of misdetection. Graphically, if we have the estimated alpha, we want to establish a bound on alpha to protect against its fault. And the table here shows the final computation of those protection level bound for alpha under different hypotheses. In particular, under the H1 faulted hypothesis, we added an additional integrity margin that depends on the failure rate of a particular fault. So in order to test our fault detection algorithm, we post-processed a SENTERA flight data with a known fault signature. The SENTERA Phoenix here uses an Eagle Tree pitot tube, and it's used for agriculture inspection mission showing on the right. This is down in Minnesota. In one of those missions, this flight in particular lasted about 50 seconds, and it crashed due to the water-plugged pitot tube. you can see that the airspeed dropped to actually negative when, even though the aircraft, based on the altitude information, was still in the air. So we test 3 different detection functions here: the innovation test, the proposed residual test, and also something we added another test called the geometric moving average residual test. Basically, it's a weighting function to weight exponential weighting function on the window of the residuals. So there, on the right, there are 3 different regions that's worth examining. We can see that innovation test on the upper graph. It's actually very sensitive to dynamic motion. There's a large S-turn, and also can before the airspeed drop, the airspeed actually increased first, then drops, right? So so it could raise false alarm because it wasn't a fall. The fall actually occurred in this red region. On the other hand, the residual-based test is less sensitive, and it only exists the limit at the end of the flight. And this geometric moving average is even less sensitive, and it provides a more superior detection capability. Lastly, we want to show how the protection level bound is used to protect synthetic alpha estimate. We plotted the state, the 2 sigma bound, and the protection level bound, and its alert limit. The protection level bound basically informs whether the system maintains its integrity, and the alpha estimate estimate seems okay, usually by the sigma bound, but it might be potentially unsafe with aggressive maneuver or associated fall at the end. And there's a PL level, right, when compared to the alert limit, can catch this sort of behavior. It can be shown basically here, right? The loss of integrity happened due to aggressive S-turn and a faulty pitot tube at the end. This can inform the system that alpha estimate is not useful in those regions. One thing I would like to emphasize is that protection level is more than just the confidence level bound. It is the largest error which may result without the required integrity risk being exceeded. So yeah, so that concludes my talk, and thank you for your time. We can move to the Q&A section.
Great, thank you, Kerry. We appreciate it. We do have one question, and for those of you viewing, if you have a question for our presenter, you can click on the Q&A button in your viewer and type your question in, and we will address that. The first question, Kerry, we have is what was the computational power and cost for implementing the fault detection system? And did you compare this to using heated tubes?
So this is a down so it's actually we post-processing the flight data, so we didn't really have really look at how computation it is whether expensive computational procedure or not, but just it's a common filter based algorithm, right? So and as long as the window of measurement is not long enough, it's not like you're using all the past measurement. I don't think computational wise is very expensive. Yeah, and I'm not sure about the power cost. Are you talking about the battery cost? I haven't looked at that, but for heated pitot tube, in this case, it's not a heated pitot tube. It's actually a really simple pitot tube system. There's no heating device on the pitot tube. Yeah. yeah, I've not done the comparison in this case.
Okay, great, thank you. Here's a question. With the pitot tube being a single point of failure, can we use GNSS as a backup airspeed monitor for safety of life?
So in this case, in order to come up a reliable air data estimate, the pitot tube is actually used as a measurement with GPS, with GNSS and the IMU to come up the synthetic air data estimate. That's why we actually have the design is actually to have 2 pitot tubes on board. So in the case of us, one pitot tube goes down, the design is to, in the paper I talked about a little more, like, basically you use the other one. Hopefully there's no common failure mode happens to both pitot tubes. And and the procedure here really, it's if we detect a single pitot tube failure, the next thing for the vehicle to do is actually to do an emergency landing. You can think about this, it's like a trade-off. Usually, if you think about drones or commercial aircraft, you can either have 1 pitot tube, 2 pitot tubes, or something called a triple redundancy. Usually you have 3 sort of air data systems. And the reason we could, basically reduce from a triple to a dual pitot tube is to leverage other sensors informations to provide this kind of redundancy. So, yeah, I think that's answered that question.
Okay, great. Let's see. How will turbulence affect the fault detection? That's a question from Sven.
Yeah, so we have not really considered turbulence effect for this study, and one of the assumptions here for the common filter to work is the wing has to be quasi-static. So if there's a large turbulence effect that's surrounded by the sensor itself, and the estimate might not be reliable, and that also might cause the fault detection to be unreliable. There are papers out there, however, that consider turbulence effect and model them as states in the common filter to counter for those. But I think it's a very limited study too. You're right. Turbulence effect is very severe to systems. It's something, I think it's like a very, it's a limitation on the system, fundamental limitation if there's a large turbulence effect. Just to give you an example, if you think about eVTOL, electrical vertical takeoff aircraft, when you take off vertically, there's going to be a huge turbulence effect, a ground effect. So in that region, you can't really rely on those, synthetic air data estimate or the data, the sensor itself, right? Those regions are just very unreliable to be operated in.
Okay, great, thank you. We have a question from Sally, who asks, the synthetic air data system, or SADS, you discussed is model-free. Do you think that model-based versus model-free has a significant impact on the ability to detect failures?
Yeah, hey, Sally. So I think it just depending on the accuracy of the model, the estimate. So the model-based usually relies on the model of the aircraft, in this case, the aerodynamic model, and the other sensors, IMU, GPS, all this to sort of estimate air data quantities. Model-free, in this case, we kind of just leverage sensor itself. We also leverage, sensor itself and the kinematic model. And the impact really, it's like how accurate the model is, if when you're using for the model-based SAS system. If, for example, over the years you have tier or something is off, you forgot to update your aerodynamic model, and then you'll have like let's say a biased estimate, which I think, yeah, it will affect your failure. But I think there's, whenever you have those estimate, you wanted to make sure, first check is to make sure your bias are consistent. There's no, the states are consistent and biased. So I don't think there's a significant impact. It's just depending on how you tune your filter, make sure your estimator works first. Then the next thing we can look at how we define the fault detection function. If the estimator is not giving the correct estimate, yeah, then that will severely affect the detection capability.
Okay, and our last question here says, do you know the likelihood of a water blockage failure mode in the different climate conditions?
So here we deal with very low cost a pitot tube system. Maybe let me show this figure here, right? Wait, what's happening? One second. Yeah, so you see here, this pitot tube is like, there's no heating system on board, right? This thing just connect to the plastic pitot tube and wired to the transducer, and put, for example, if you have a Pixhawk, it's really connect to the Pixhawk, right? So for low-cost UAS system, right, in United States, you can operate up to 400 meters. That's the requirement if you, under Part 107. So actually, I talked to people that they recommend you not to fly any UAS under any raining conditions, right? So you see when they fly out there, it's actually sunny. So when it's raining or when it's a foggy day, most likely you might just run into this kind of problem. So it is actually a very big issue if you wanted to constantly run this under any sort of climate condition. And if we talk about, I'm going off topic a little bit. If you're going to talk about commercial aircraft, right? On the commercial aircraft, they have, heating system and, backup sensors. So in that case, if you have a water blockage for usually it's like, analyzed or studied with those commercial aircraft, like, so you don't really see a water blockage for in that case. But for the smaller UAS, this happens all the time, and you don't hear it because people don't like talk about their failures. That's what I think why you don't hear it.
Okay, great. Well, thank you so much, Carrie. We appreciate your time, and we know you're very busy, and appreciate all the preparation you've put into today's webinar. Again, if you have any questions, and Carrie, if you could pull up your slide there with your contact information, feel free to contact Dr. Sun, and this webinar will be posted on our website, available with the download of the full paper, which was just published in our journal, and you can read all the details there. So again, Carrie, thank you for providing this webinar for us, and thank you for joining us.
Yeah, thank you for this opportunity. And thank you for the audience for attending this seminar.